Okay, it should be on now.
Okay, so let's begin with the lecture.
Okay, thank you. Okay, so just a reminder of what we discussed yesterday. We were looking at perturbation theory in Schwarzschild spacetime. And in Schwarzschild spacetime, the linearized Einstein equations, and therefore the second order and third order and all order Einstein equations, are separable by using a basis of tensor spherical harmonics and a Fourier transform. And so when we started with 10 coupled 3+1 PDEs in TR theta phi, once we use our separability ansatz, we end up with 7 coupled ODEs in R for each LM mode, well, each LM omega mode. So this is for each LM omega. 7 coupled ODEs for the even parity coefficients, and 3 coupled ODEs for the odd parity coefficients. And that's without using any of our gauge freedom, so you can reduce that number of equations using gauge freedom. So now what I want to briefly describe is the boundary conditions that we place on these coefficients. So we're working with variables, remember, H even, N, L, M, omega, where the even here stands for TT, TR, RR, T plus, R plus, and what else? Plus, and circle. So that's 3, 5, 7, perfect. So we have 7 of these fields, even parity fields. They're just functions of R. And then we have 3 odd parity fields, T minus, R minus, and just minus. So for each of these fields, it depends on your gauge choice, but if you're in a nice gauge, like the Lorentz gauge, for example, each of these fields satisfies kind of natural boundary conditions. Is there anyone here who hasn't seen Penrose diagrams? Okay, everyone has seen Penrose diagrams. Okay, so let's draw the Penrose diagram for Schwarzschild. So we've got scribe plus here, we've got H plus here. That's not much like a scribe. We've got an advanced time coordinate V that runs along the future horizon, and we've got a retarded time coordinate U that runs along scribe plus. Where, remember, V is T plus R star, the tortoise coordinate, and U is T minus R star. So, really, what we're talking about for these variables is something that gives you regularity at these 2 surfaces. And basically what we want is waves traveling out to scribe plus and waves traveling in to the horizon. This looks like it's connecting to the V arrow, but it shouldn't be. So we want ingoing waves that are nice and regular here. We want outgoing waves that are nice and regular there. These solutions for a fixed value of omega are actually going to be singular on the past horizon and scribe minus, but we don't really care. Past horizon and scribe minus are not real locations in space-time. What we care about is the physical horizon and future null infinity. And if, depending on the problem, usually once you integrate over omega, you recover something that's regular here anyway. But that depends on the problem. Okay, so what I want to describe is outgoing wave at scribe plus and ingoing wave at the horizon. So let's say I'm working with retarded coordinates at scribe plus. So in fact, not TT, TR, RR, but UU, UR, RR. Let's look at just the first order field. And yeah, I'm going to be in the time domain first, and then I'm going to translate that into the frequency domain. So I'm looking at the time domain field at large r. So r goes towards infinity. And for this to be describing an outgoing wave, what I want is that this is some function of retarded time divided by r. So this is a nice, well-behaved field at scri plus. If it's really a wavy field, then this capital A is oscillating as a function of retarded time. So there's also subleading terms, 1 over r squared, etc. So if this is the behavior of the time domain field, what does this imply about the frequency domain field? There's a reason I'm stopping at 1 here, I'm not going to 2. So in the self-force context, at second order, usually this doesn't work at all. Everything goes a bit crazy. So I'm working at first order, and I'm assuming sufficiently rapid fall off of the stress energy tensor, so that you're basically in vacuum when you reach infinity. Okay, so this is just a function of r now, not a function of u. And if I want to recover this once I multiply by e to the minus I omega t, then I have to have a very specific dependence on r at large r. So remember, in the time domain solution, I take this and I multiply by that. So the only way I'm going to get a nice, smooth oscillatory function of u to recover this form is if I put in plus I omega r star over r times some coefficient. This a is like the frequency domain version of that a. This is just a constant. So this is a wave traveling outwards towards larger r. And you can see once I multiply by this to get a time domain field, this just becomes e to the I omega u. So this is how we choose our outgoing boundary conditions at scri plus. Then and it's the same for all the coefficients there. So ur, rr, u plus, r plus, etc. Just with different constants in front. And we would say this a is the amplitude of the field at infinity. Okay, now how about at the horizon? So say we're looking at the VV component in ingoing Eddington-Finkelstein coordinates. Yeah. So I want a field in the frequency domain such that when I multiply by the Fourier factor, I get something nice and smooth as a function of u. So if I multiply by this, then I get e to the minus I omega t plus I omega r star, which is just e to the minus I omega u. So I just want something that combines into u once I've multiplied by this. Okay, so for the horizon, first in the time domain, we want this to be some smooth function, and here I can just substitute 2m, some smooth function of, do I put L's in there? Yeah, Lm. Some smooth function of v along the horizon. Or if I want to say that this r approaching 2m, then I want it to be this plus something of order r minus 2m at fixed values of v. So this is just describing a wave moving up along v. But it doesn't really matter here, even if it's a wave, it's just something that's smooth at the future horizon. So same idea. When we go to the frequency domain, we look at h1 Lm omega Bv. It's now a function just of r. I want this to be some constant. let's say B0. And let me actually put a 0 on this to indicate that it's just some constant. Times something where when I multiply by the Fourier factor again, I get a nice smooth function of V. So to do that, it's the same idea, except now with a minus sign rather than the plus sign that we had there. Plus things of order r minus 2m. So once I multiply by this, I get e to the minus I omega v, which is a nice smooth function along the horizon. Okay. Now, as I mentioned, this is really specific to first order, and it assumes nice smooth sources as well. So at first order, everything separates, everything decouples. I can solve for an individual LM omega mode. I can solve for the next individual LM omega mode, and I can solve for all of them separately from each other. They don't depend on each other. That's still true at second order, but remember that the linearized Einstein tensor acting on H2 LM omega is sourced by quadratic things. G2 LM omega plus a stressed energy term, but let's ignore that. I'm interested just in the quadratic terms. But this involves not just the same LM omega, but every single other LM omega. So I discussed that about the L's and M's, but it's also true for the omegas. So in here, I'm really putting the physical field, H1. This is a Fourier transform and a sum over L and M. This is a Fourier transform and a sum over L and M. And this guy depends on every single omega of each of these two, and every single L and M of this, and every single L and M of this. So even though you have nice decoupling at first order, at second order, you have infinite coupling to get anything, to get an individual LM omega mode at second order. I'll show you some explicit expressions in Mathematica later in the lecture. Okay. Yes? So it works in kind of the naive way, as far as I remember. If you're looking at an even piece of G2, that can come from odd times odd, even times even. If you're looking at an odd piece of G2, it has to be odd times even. I think I'm right, but don't totally trust that. I could be wrong. I think that's true, though. Okay, now I mentioned at the end of yesterday's lecture that usually when people are doing black hole perturbation theory, they are not directly solving the perturbative Einstein equations. They're mostly indirectly solving the perturbative Einstein equations by using the Tucholsky equation. And Schwarzschild people will often use the Reggie, Wheeler, and Zerilli equations instead. But I don't have time to cover that, so I'll just cover the Tucholsky equation, which you can do in Schwarzschild and in Kerr. So the Tucholsky equation is a separable equation for a single scalar field. And it can actually be for two different scalar fields, but it's just two different equations. So these are psi 0 and psi 4. And this is the nth order psi 0 and the nth order psi 4. So these are complex scalar fields, so two functions, as opposed to the 10 functions we were trying to solve over there. And these two functions give you most, but not all, of the metric perturbation. And the important thing is, these are separable not just in Schwarzschild, but also in Kerr. So you have separable scalar field equation, complex scalar field equation, in Kerr, from which you can reconstruct most of the metric perturbation. So the Tucholsky equation is very powerful and very convenient, which is why people are generally using it. I'd say outside of self-force applications, probably 90% of the time when people are doing black hole perturbation theory, they're solving the Tucholsky equation. In self-force, things are a bit more complicated. Yeah.
So when we talk about Regiment equation,
Yeah.
so in that case, central black hole is Schwarzschild. So
Yeah.
if the secondary particle is supposedly it has spins, it can also like Regiment push up point, right?
Reggie Wheeler you can still use for a spinning particle, yeah. Reggie Wheeler, if you're doing self-force, Reggie Wheeler gives you very nasty metric perturbations. Reggie Wheeler is quite pathological. The gauge that I'm going to introduce a little bit later, coming from Tucholsky equation, is also very pathological in self-force applications, but it's still so convenient that we usually use it anyway and then just deal with the pathologies. Okay, so these scalars, has everyone been introduced just to the Weyl scalars? Or are there people who haven't been introduced to the Weyl scalars? Okay, a few people. Okay, so these are projections of the Weyl tensor. Has everyone been introduced to the Weyl tensor? So the Weyl tensor is the trace-free piece of the Riemann tensor. So it's the piece of the Riemann tensor where if I trace over any two indices, I get 0. And it's denoted C, alpha, beta, gamma, delta. If you're in vacuum, it's just identically equal to the Riemann tensor. So this is the Weyl tensor. And we construct scalars from it, Weyl scalars, by introducing a null tetrad. L alpha, N alpha, M alpha, M bar alpha. Previously, I was using bar for trace reversal. This bar denotes complex conjugation. So this is a complex vector, and this is its complex conjugate. Each of these is a null vector. So we have L alpha equals 0, N alpha equals 0, etc. They're all null. And most of them are orthogonal to each other, meaning if I contract N with M, I get 0. If I contract L with M bar, I get 0. There's only 2 non-zero contractions, which are L alpha, N alpha is -1, and M alpha, M bar alpha is +1. So in this basis, the metric looks very, very simple. It looks like Minkowski. But the important thing about this for us is how we use it to construct the Weyl scalars. So these are not unique. They're just defined by these equations, which don't fully determine them. So you have some freedom in how you construct these null tetrads, which becomes important because then usually you're looking for objects that are invariant under changes of the tetrad. And linear order and perturbation theory, psi 4 and psi 0 are both going to be independent of at least infinitesimal changes in the tetrad. They won't be invariant under big transformations of the tetrad. Okay, now, actually let me draw another Penrose diagram. Okay, I don't want to specify whether I'm in Schwarzschild or Kerr, so I won't draw the interior. L is a radially outgoing null vector. N is a radially ingoing null vector. M is tangent to the sphere of constant T and R, say. And so is M bar. So let me just write the examples in flat space-time to give you some sense of what these things are. So L alpha is 1 over root 2, 1, 1, 0, 0 in TR theta phi coordinates. N alpha is 1 over root 2, 1, minus 1, 0, 0. M alpha is 1 over root 2 R, 0, 0, 1, I over sine theta. And M bar is just the complex conjugate of that, so I just changed the sign here. So the important thing is this is radially outgoing, this is radially ingoing, this is tangent to the sphere, and it's complex. So the Weyl scalars, psi 0 and psi 4, are constructed by contracting tetrad legs against the Weyl tensor to construct scalars. Now what I'm going to do is put a hat to indicate that this is the Weyl scalar of the full spacetime, the exact spacetime. This is not yet perturbatively expanded. Same thing here, C hat, and we've got L hat, alpha, M hat, beta, L hat, gamma, M hat, delta, and psi 4. We just change L to N and M to M bar. So C hat, alpha, beta, gamma, delta, N hat, alpha, M bar hat, beta, N hat, gamma, M bar hat, delta. Okay, now one thing to note is terminology. This is called a spin +2 field. So indicate that this is spin 2. And then psi 4 is spin -2. And basically, to count the spin of an object, you just look for the number of m's. Each m gives you a +1. Each m bar gives you a -1. And so we have spin 2 because we have 2 m's. We have spin -2 because we have 2 m bars. Now what I'm going to do, well, actually, I'll mention one thing. So not only does psi 4 or psi 0, either one of them, in the perturbative context, not only does each one encode most of the metric perturbation, even in the fully nonlinear context, psi 4 directly encodes the waveform at infinity. So if we take psi 4 hat, R goes to infinity along lines of constant u, this basically is the second derivative of the waveform. So here h is the stress, or sorry, the strain. So psi 4 is directly related to the waveform. The waveform is basically 2 time integrals of psi 4. Okay, now what I'm going to do is perturbatively expand psi 4 or psi 0, both or either. And I'm going to work in Kerr. So in Kerr, I write that psi hat. Let me first start by writing the expansions of the individual pieces that go into it. So C hat, alpha, beta, gamma, delta is the background, C, alpha, beta, gamma, delta. Remember, Kerr is a vacuum metric, so this background C is just a Riemann tensor of Kerr. plus order epsilon, C1, alpha, beta, gamma, delta. And for this portion, let me just focus on linear order. You can extend everything to second order, but for Tucholsky, I'll just focus on linear order. And then similarly, each of the tetrad legs gets expanded. So each one is expanded in the same way. Now, usually in the literature, when people are talking about what tetrad they are using, they are specifying the background tetrad. They're usually not specifying the perturbed tetrad. And when I mentioned psi 0 and psi 4 are invariant under changes of the tetrad, what I meant was under changes of the perturbed beats. Infinitesimal transformation of the tetrad, an infinitesimal rotation of the tetrad. So you can choose these in different ways while still satisfying your defining equations. And usually we're looking for things that don't change when I change this. Now, psi 0, I'm going to write, and again, I'm going to stick to first order here. I'm going to write in two ways. So we have C1, alpha, beta, gamma, delta, L, alpha, M, beta, L, alpha, M, delta. And now generically, you would expect I'd have a second term coming from perturbations of the tetrad legs. So I would expect a term that's the background C multiplying linear perturbations, L1, M1, etc. But in Kerr, that doesn't happen. Psi 0 only involves the background tetrad legs, which is why it's kind of trivially invariant under a change of the perturbative tetrad. And you'll very often also see this written in a more abstract form as some linear operator, script T, or calligraphic T, acting on H. So this is just, you don't need to know what this is, it doesn't matter. This is just a linear operator. It involves up to two derivatives, so it's a linear second order differential operator. Psi 4, exactly the same story. I'll skip the expression in terms of C1. Let's write it as just a linear operator, T4, acting on H1. Again, it's second order linear differential operator. This might be hard for people to see from the back. There we go. Okay. Now, what Tucholsky discovered, so this whole description of tetrads and Weyl scalars, all this stuff, this all comes from Newman and Penrose, yeah? Yes. Yeah. Yeah, so it's just because of the particular contractions that appear that, so first you write down this in the most generic form, and then it's the particular contractions that appear. I'd have to double check if it's true for every vacuum background. That might be the case. Maybe. I don't know, I'd have to double check that. Yep. Yep.
The tangent space to a real manifold is a real vector space. So do these tetrads actually belong to the tangent space?
Yeah. 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 So yeah, these are not, okay, maybe they're not tangent to the ordinary tangent space, or not elements of the ordinary tangent space, because they're not tangent to real curves in the manifold. Yeah, in a complexified tangent space. Yeah, like you can write this as a real part and an imaginary part, and then we have two real vector fields, and one of them I multiply by I. And then each of the two real vector fields are in the real tangent space. Okay, so Newman and Penrose already invented all this technology earlier, before Tucholsky. But what Tucholsky found that was miraculous is that psi 0, 1 and psi 4, 1 satisfy decoupled equations, meaning I don't have equations for psi 0 that involve psi 4 and vice versa. And you notice I skipped a whole bunch of numbers. I didn't write down psi 1, psi 2, psi 3. Kind of generically, you might expect that if I write down a field equation for psi 0, it depends on all the other ones. But psi 0 and psi 4 decouple not only from each other, they decouple from everything else. So they satisfy equations just on their own that are decoupled. And those equations are also separable. So these satisfy decoupled, separable equations. And those equations are called the Tucholsky equation. Yeah.
What are the equations in this case? Like the Riemann tensor or the Y tensors component. So, like, are you like using the second Bianchi identity to calculate the?
Yeah. So there's multiple different derivations of the Tucholsky equation. One is really based on the Bianchi identity. Others use the Bianchi identity, but the simplest conceptual way to derive them is from the Penrose wave equation. Which has the form of box C alpha beta gamma delta plus some stuff that's quadratic in C equal to some stuff constructed from the stress energy tensor. So you can take this Penrose wave equation. The right-hand side is very long to write out. It's relatively short, but I don't have it written down. And then just contract this whole thing with the tetrad legs you want in order to end up getting either psi 0 or psi 4 in there. So you commute your derivatives with the tetrad legs. You move the tetrad legs in to contract with this. You end up with psi 0 or psi 4. You do a whole bunch of complicated manipulations, and out comes the Tucholsky equation. So you use the Einstein equation in constructing this source. I think that's the only way you use it. So over here, you'll generically have a whole bunch of Ricci tensor things. Then you relate those to the stress energy tensor using the Einstein equations. But yeah, this Penrose wave equation is not very well known, but it's pretty amazing. It's a quite simple equation for the curvature itself, not for the metric. Okay. Now these equations I'm going to write in very abstract form, but I'm going to show you them in Mathematica later. So I've got a linear operator O, subscript 0, acting on psi 0, 1. And the source for it is another linear operator acting on the first order stress energy tensor. So this is second order linear differential operator. This is second order linear differential operator. And then same story for psi 4. I guess to be consistent, I should put square brackets here. They're not usually drawn in these equations. Okay, so this is kind of a wave operator. It's very similar to wave operator, although it doesn't have all the nice properties of a D'Alembert. But it's basically a hyperbolic operator. And same with this, And these are just, again, second-order differential linear operators. Now, the way you separate these equations, you can't, unless you're in Schwarzschild. If you're in Schwarzschild, you can use the same kind of strategy as we did for the linearized Einstein equation. First, decompose in some spherical harmonics. In this case, they would be called spin-weighted spherical harmonics, where the spin weight would be the spin weight I mentioned for psi 0 or psi 4, so spin plus 2 minus 2. You decompose into spin-weighted spherical harmonics. That would give you 1 plus 1 PDEs in T and R. Then you could further do a Fourier transform if you wanted to, but you wouldn't need to. You could just solve the PDEs. Do a Fourier transform to get to ODEs. In Kerr, you actually cannot separate the field equations, the Tucholsky equations, using just spherical harmonics. You have to actually go to the frequency domain as part of your separability ansatz. It's only separable in the frequency domain. So the ansatz looks like this. We have Fourier transform. We have sum over L and M. Typically, the radial coefficients that are just functions of R are written with the spin weight there, and they're written as capital R. And they depend on L, M, and omega. Put a 1 there. So these are just functions of R. Then we've got our angular dependence. The phi dependence is the same as Schwarzschild's. It's just the usual e to the im phi that appears in spherical harmonics. And the reason it's the same as in Schwarzschild is that Kerr is axially symmetric. But the reason this is not a nice simple Legendre polynomial is that Kerr is not spherically symmetric. Okay, and then I've got the e to the minus I omega t. Here, I'm using Boyer-Lindquist coordinates, t, r, theta, phi. You can decompose in other coordinates as well. Now this thing here is the funny bit. This is spin-weighted spheroidal harmonics. These are not known in closed form. They're only known as the solution to an ODE in theta. And as I mentioned, you can't decompose into angular harmonics, but also decomposing into Fourier harmonics, because your angular harmonic here actually depends on the frequency. Same thing for psi 4, except that to separate the equation, the Tucholsky equation in Kerr, you need to introduce an overall factor in your decomposition. It's 1 over r to the minus I a cos theta. A is the spin parameter of the Kerr black hole, raised to the power of 4, and then everything else is the same. D omega, with some limits on this integral. Sum over L and M. We've got minus 2 as the spin weight on capital R and capital S. L, M, omega, R times minus 2 S, L, M, omega, theta, e to the im phi, e to the minus I omega t. So you see that in Schwarzschild, this just becomes a power of R. This theta dependence drops out. So in Schwarzschild, you don't need to introduce this overall to separate the Tucholsky equation. But in Kerr, you need to introduce it, otherwise the Tucholsky equation doesn't separate. Now once you've done that, what you end up with is ODEs for these radial coefficients. So you have, question, yeah.
I
at infinity. Yeah.
So what will intuitively psi for 1 represent, like for psi 0?
So psi 4, okay, if we're in a Kerr background, there is no wave in the background. So psi 4 1 is then the leading order part of the wave. Psi 0 is not so naturally related to the outgoing wave. Psi 0 is very naturally related to the ingoing wave at the horizon. Okay, so we get our radial ODEs, which I'm going to write in a combined form. I'm going to put a spin weight to indicate this could be plus or minus 2. This is acting on my radial coefficients, Lm omega. And we have some source. Lm omega, constructed from T1. So this is just the full T1 with all its angular dependence, and then I integrate against the harmonics over there to get this coefficient, curly S, Lm omega. So this thing is basically, second radial derivative times something. Let me not call it A. C plus first radial derivative times something plus, a potential term. So this is a quite simple second order operator, radial operator. Yeah.
So I have a question that's
Yeah.
so in black hole propagation theory, what is this equation? Is it the case that this element forms a complete basis, that is why we are using it, or it naturally comes in the mathematical formulation?
So it does form a complete basis for functions of theta, and it is orthonormal. So it provides a nice basis, but that's not how it was found. It was found by looking for the function that separates the Tucholsky equation.
So why I'm asking this because I always get confused between NPM modes coming from NPM and comparing that to each modes. Because in NPM we use spherical harmonics.
Yeah.
Of course, we can decompose that in spherical harmonics.
Yeah.
But I mean, the motivation of using this was not clear.
It's just to separate the equations. That's the only motivation. You'd never have any other reason to ever think about this. Because spin-weighted spherical harmonics are way nicer. So if you can use those, you do use those. This is only for separability. And in fact, to generate a waveform, it's annoying to have this involved because it depends on omega. And in the Emery case, we have an in-spiral. The frequencies are evolving with time. And so then you need to be calculating this spin-weighted spheroidal harmonic at each time step and evolving it as the frequency evolves, which is a ridiculous thing to do. So instead, the much better thing to do is actually to re-expand onto a basis of spin-weighted spherical harmonics. Yeah. Okay. Now, the final thing to note is that I said that you not only get the waveform from psi 4, you get most of the metric perturbation. So what do I mean by that? Well, in vacuum, you actually get the entire metric perturbation from psi 4. So this is 2 times the real part of S dagger. And actually, this S operator that I had in the sources, it actually has 2 indices that I was just ignoring. So I'm restoring those so that I have the same indices on right and left. And this dagger is the adjoint. Is everyone familiar with adjoint just from linear algebra? No? Okay, so the adjoint, just think of doing an integral over space-time. So this is the covariant volume element. If we have some function u and then some operator, say d, acting on, okay, that v looks, it's a bad choice, let me make w. Then this is d dagger acting on u times w. So if you integrate by parts and move the derivatives in this operator d, move those onto u, then whatever you're left with acting on u is by definition the adjoint. And this is a kind of inner product, so this would follow what you've learned in quantum mechanics. Okay, now this adjoint operator is not acting directly on psi 4. It's acting on another scalar field called the Hertz potential. Now the Hertz potential satisfies yet another equation where we act with, I guess I'm working with psi 0 rather than psi 4 here. It works either way. So we take this S operator that gives us the source in the Tucholsky equation. We act on this Hertz potential. We take the complex conjugate of that whole thing. We then act with the operator that takes you from a metric perturbation to psi 0. Then this has to be equal to psi 0, 1. So this makes sense. This is just saying, if I have this metric perturbation, and from it I construct psi 0, well then I should have psi 0, right? So this is saying that the psi 0 in the physical space-time should be equal to what I get when I take this metric perturbation and act on it with this curly T operator. And amazingly, this combination of operators here is actually incredibly simple. Each individual operator is quite complicated, but this particular combination is basically L alpha partial alpha raised to the power of 4. It's just 4 derivatives in the L direction. Now, this is in vacuum. This gives you the full metric perturbation in vacuum. If you're not in vacuum, you have to add what is called a corrector tensor. This is only in non-vacuum. And amazingly, this corrector tensor also satisfies quite simple radial ODEs along the curves generated by L. So, radially outgoing towards infinity. Okay, I won't go much into either of these things, but this is what we use in cell force calculations. We start with psi 0 or psi 4. We calculate a Hertz potential. From that, we calculate a metric perturbation. From that, we calculate the self force or other quantities. In many calculations, you can get away with never reconstructing H. You can just work with Tucholsky. That's only ever true at first order. Once you go to second order, you can never do that. But at first order, oftentimes, you can just work with the Tucholsky solution and ignore H entirely. Okay. Now, I was going to switch over to Mathematica for a little bit. Before I change topics entirely. Yes?
So I just have one question regarding this spheroidal harmonics.
Yeah.
So is there any notion of even parity or odd parity for spheroidal harmonics?
Okay, so spheroidal harmonics, if you include that e to the im phi together with it as your angular harmonic, spheroidal harmonics, if you're in Schwarzschild, reduce to spin-weighted spherical harmonics. And And that's because the omega dependence of the spheroidal harmonic always comes in the form A times omega. And when A goes to 0, the omega dependence drops out, and you get back to spin-weighted spherical harmonics. Now, once you're working with spin-weighted spherical harmonics, even parity and odd parity are usually of the form real part of something minus imaginary part of something. It's complex combinations. So even parity, odd parity is less intuitive in spin-weighted spherical, and even less intuitive with spin-weighted spheroidal. Yeah. Okay, so I'm going to start actually by backtracking to the linearized Einstein equations. How many of you have installed packages? Okay, almost everybody. And I'm assuming that anyone who didn't already have X-tensor installed has not now installed it. Okay, so I'm going to demonstrate this perturbation equations package, but if you don't have X-tensor installed, then it takes a little bit of time to install it, so don't bother unless you want to. But I mostly want to just actually show you some of those equations I was writing down. Everything I've been writing has been very schematic. Here I can actually just show you all the equations. So just as a reminder, these are the packages I had suggested everybody install. Here I'm just loading the package, and you see it has to start with exact. Okay, now the expressions that come out of this package are often not pre-simplified. They're a bit of a mess to start. So here I'm just defining something to simplify them, to make them a bit more readable. And here I'm defining a way to convert from X-tensor expressions to ordinary Mathematica expressions. And I guess we can send around these notebooks to the entire class after the lecture. Okay, so let's look at the linearized Einstein equation. Well, let me first run this section. So this package is designed to give you all the field equations you could be interested in, except that it doesn't include Reggie-Wheeler equations, but almost all the field equations that you could be interested in, and in almost all of the conventions you might be interested in. So Schwarzschild linear operator loads the linearized Einstein tensor. Here that is denoted dg, which is another notation that I use for G1 in a lot of my papers. So this is just the linearized Einstein tensor. And you specify what you want. You can ask for linearized Einstein tensor. You can ask for linearized Riemann tensor. You can ask for linearized Tucholsky. Then you get to choose what gauge you want. You can choose the Lorentz gauge. You can choose the Reggie-Wheeler gauge. You can choose something else that I should have mentioned related to metric reconstruction. So this S dagger phi plus x gives us a perturbation in the ingoing radiation gauge, IRG, or the outgoing radiation gauge, ORG, where those are defined by the conditions H alpha beta L beta is equal to 0. That's the IRG. Or H alpha beta N beta equal to 0. That's the ORG. Might be paying enough attention to think these names are very strange, because L is the outgoing null vector, N is the ingoing null vector. So usually, you would think that this would be giving you an outgoing radiation in a nice form, and this would be giving us an ingoing radiation in a nice form. The reason they're given these names is just a particular form that comes out of metric reconstruction. Specific to metric reconstruction, you get a nice outgoing form of the solution. Like if you have an outgoing wave, it takes a nice simple form in this gauge. If you have an ingoing wave, it takes a nice simple form in this gauge. Specifically if you're doing metric reconstruction like that. Okay, so yeah, you can pick ingoing or outgoing radiation gauge as your gauge choice. And then you get to pick different basis choices. So you can use the tensor harmonics, you can use spin-weighted harmonics, you can use different choices of things. And most of the expressions are given in terms of this quantity mu, which is a certain combination of L and S. So L and the spin weight. Okay, so here I'm looking at the tensor harmonic coefficients. So this is the TT component of the linearized Einstein tensor, constructed from the even modes of H. And this is a given LM mode of that quantity. So I want DG to indicate that I want the linearized Einstein tensor. I'm putting this in a generic gauge, so this expression is true in every gauge. And tensor means tensor harmonics and TR coordinates. And then here I'm indicating that I want the TT component. So this is the TT component of the mode decomposed, tensor spherical harmonic decomposed linearized Einstein operator. And you see it only involves even parity things, H plus, H circle, HR plus, etc. And it involves up to 2 derivatives. This number 1 means an derivative. If it were 0, it would be a T derivative. You can convert to the frequency domain inside the package, but I'm just going to show you the time domain solutions. And if you want to see it in ordinary Mathematica form, you can just apply this replacement rule that I showed you up above. And so now it's just ordinary derivatives of ordinary Mathematica functions. Similarly, here's the TR component. Again, it only involves even parity metric perturbation coefficients. It involves, in this case, no second derivative except a mixed derivative that's 1 T derivative and 1 R derivative. And this is kind of the generic structure. You have up to 2 derivatives. They can be T derivatives or R derivatives. And you tend to get dependent on all the different parity pieces in each of these pieces of the Einstein tensor. Then odd parity. So here I'm looking at the T minus piece of the Einstein tensor. Same idea, up to 2 derivatives, and involving all the odd parity pieces of the metric perturbation. Now, let's say we want to go to second order, and we want that quadratic source term. And I want to express it in terms of first order modes. So we get that using this Schwarzschild quadratic operator. Everything here is going to be written in terms of this coupling coefficient that is an integral of 3 spin-weighted harmonics. So when I was deriving all these equations, I found this. By the way, my student, Andrew Spires, is the one who actually wrote 95% of this package. When I derived this, I just found it much more convenient to use spin-weighted harmonics. Even when I was starting from tensor harmonics, I would then just convert everything to spin-weighted harmonics, decompose, then convert back to tensor harmonics. The spin-weighted harmonics are often nicer to work with. Okay, so let's look at an example. So this is the TT component, LM mode, of this quadratic Einstein operator, which in this package is denoted D2G. That's for this delta squared G. Again, this is a generic gauge, and again, I'm getting the tensor harmonic coefficients in T and R coordinates. And what it's being outputted here is what you get from individual first order modes. So you put in 2 first order modes, out pops what I'm going to show you. if you then want the actual full second order source, you need to then sum over all those first order modes. So just for comparison, let's scroll back up. This was what we had at first order, this whole two-line expression. This is what we have at second order. So it's much worse. And then you need to sum over an infinite number of modes, products of infinitely many modes. Okay, now let's look at the Tucholsky equation. So this is the spin weight plus 2 Tucholsky equation. Here it's a very nice simple equation. See why everybody knows and loves the Tucholsky equation. Fits on one line, unlike the linearized Einstein tensor. Involves up to 2 radial derivatives and simple combinations of the frequency and spin weight. This is automatically in the frequency domain in this package. Version. Okay, so I'm just showing you this in case you haven't seen these equations before. I'm sure probably nobody in this room has seen this equation before, but some of you probably have also not seen even the Tucholsky equation. Okay, so if you have Xtensor installed, I would recommend just playing around with this package. It's incredibly useful if you're, first off, if you're just transforming between different conventions, different bases, but also if you just want the second order quadratic Einstein tensor, and otherwise you'd have to build this complicated expression yourself, which would take several months. Okay, so now I'm going to switch to something that will ultimately lead to generating a 0 PA waveform by the end of Friday. So here, the main thing to install or to load is the Tucholsky package. So everyone should hopefully have already installed that. And you can actually try to reproduce what I'm doing in this first section today. So ultimately, we want a sourced solution that's sourced by the secondary small body orbiting around. But first, let's just look at the homogeneous solutions, because we haven't yet introduced the source, the point particle, in the lectures. So I'm going to look at the independent spin minus solutions to the source-free radial Tucholsky equation. I'm going to specialize to Schwarzschild just because things are simpler. And I'm going to look at equals to m2 and just a randomly chosen value of the frequency. So the Tucholsky equation, which was behind the board, is a second order ODE, which means we have 2 linearly independent solutions, homogeneous solutions. So the ones that we use when we want to impose our physical boundary conditions at Scri plus and H plus are called the up solution and the in solution. So up means you have a solution that's purely outgoing towards Scri plus. So this is up. And the thing that's purely ingoing to the horizon is called in. There's actually 4 different choices of basis function people use, which are in, up, out, down. But these are the ones that are giving you the physical behavior at Scri plus and at the horizon. So here is the behavior of near infinity for large r. So we have that same e to the I omega r star that I mentioned for the metric perturbation. So this is indicating an outgoing wave. And here I'm looking at spin weight minus 2, which is psi 4. And you remember in the separability ansatz, which I think is behind the board now, in the separability ansatz, I introduced that seemingly random factor of 1 over r minus ia cos theta to the power 4. That r to the 4 is what is giving me this silly r cubed. So the radial homogeneous solution, by convention, blows up like r cubed at large r, but the actual physical psi 4 is 1 over r to the 4 times this. So it's falling off like 1 over r. Then the in solution is the one that's nice at the horizon. So it's ingoing, meaning like for the metric perturbation, you have an e to the minus I omega r star. And then just by nature of the Tucholsky equation, you end up with this random factor that vanishes at the horizon. Okay, so to get the homogeneous solutions, you use this function Tucholsky radial. Here I'm specifying spin weight minus 2, L equals 2, M equals 2. I'm specializing to Schwarzschild, so A equals 0. And here's my frequency 0.3. Now this introduces simultaneously the in solution and the up solution. So if I want one or the other, I call them like this. Now, this Tucholsky package is very good and fast at doing certain things. It is not that fast to generate this as a function of R for lots of different values of R. So for example, I want to plot the in solution and the up solution as functions of R. If I just tell Mathematica, plot it, it's going to take a really long time. Because really, this Tucholsky package is optimized to give you just the amplitudes at infinity and the amplitudes at the horizon, not to get the solution everywhere as a function of R. So what I'm going to do is pre-compute some data on a grid of R values. So here I'm starting from very near R equals 2, and I'm going up by 0.5 m for a few hundred points. And here I'm constructing a list where the first component is the value of R, and the second component is the real part of the up solution. And this cube here is dividing out that R cubed, so that I'm getting something that's going to a constant at infinity rather than blowing up like R cubed at infinity. And same thing to construct the imaginary part of the solution. Now I want to compare that to the e to the plus I omega r star, that is the asymptotic large R behavior. So I'm going to define R star, and now I'm going to plot my data, the real part of the up solution, and compare that to just the real part of that exponential. And you see they overlap extremely well, even at relatively small values of R. So they're already overlapping pretty well at R equals 30 or something, even though this is supposed to be a large R limit behavior. And then once you're very, very close, they look quite different. And so yeah, this is our outgoing traveling wave here. I don't know what this is doing. Okay, now I want to do the same thing for the in solution. I want to plot it near the horizon to see this nice ingoing wave. Now, to get anywhere close to the horizon in terms of R star, so we have this e to the minus I omega r star, and so we need to see those nice oscillations as a function of R star. To get to any significant value of R star, really, 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 really close to R equals 2m. So here I'm plotting, or I'm tabulating a few values of R star for different values of R. So R equals 2.1, 2.01, 2.001, etc. And you see, even when I'm 5 digits deep, I'm only 0.0001 away from R equals 2m. Even then, R star, its magnitude is not very big. So you need to get really, really, really close to R equals 2m to actually see these oscillations as functions of R star. So what I'm going to do instead is directly plot as a function of R star. And so for that, I'm going to calculate R as a function of R star, because the Tucholsky radial solution is being output as a function of R, not as a function of R star. So here I'm defining R as a function of R star. I'm again generating data, but now the x value here is R star rather than R. And I'm going to plot that alongside just this exponential, e to the minus I omega r star. And so again, you see they overlap extremely well once r star is sufficiently negative. And then they totally disagree once you get above r star equals 0. Okay, so in order to ultimately generate a 0 PA waveform, I would definitely suggest you try to reproduce this or just start playing around with the package. And then by the end of Friday, we will have a 0 PA waveform, and then all this notebook. And you can compare it against what you've done. Okay, I've still got about 20 minutes, but I am way, way behind where I wanted to be at this point, because today's lecture was supposed to be on cell force. I was supposed to finish black hole perturbation theory yesterday. But I think this is probably more useful for 99% of people than all the stuff I was going to say about cell force, which was very much like foundational first principles of cell force equations. Okay, so I'm going to switch back to the blackboard, and I am going to move on to exactly what I just mentioned, kind of the foundations of cell force theory. Let's see how far I can get in the next 17 minutes. But while I'm just erasing, are there any questions on this? In Schwarzschild. Yeah. Yes. Yeah. So you can always just do it numerically if it's difficult. So you know the spherical harmonics are a complete orthogonal basis. So you just integrate the stress energy tensor against one of the basis functions. Although I mean I say that you can just do that. Doing that is actually one of the hardest parts of second order cell force calculations, because we have a very nasty thing we're trying to integrate over. A very nasty thing that takes up many, many pages of Mathematica and is extremely singular at one point. And so numerically integrating against a spherical harmonic is tough. Okay, I'm going to change topics entirely to start getting into cell force theory. So the next subject here is just the basic idea of how do I introduce a small object into a space-time? How do I formulate the Einstein equations properly when I have a very small object in some external space-time? So say I've got some blob of matter with total mass little m, or it could be a black hole, it could be anything. I am going to assume that it's compact, meaning that its spatial size is comparable to its mass. We got some little blob, and it's very small compared to whatever the external length scale is. So the scale of other stuff is much, much bigger than the scale of the small object. So in an emery, this scale is the large mass. Unless the bodies are very, very widely separated, then you're basically in the PN regime, and the scale is the orbital separation. So we have L much, much bigger than M. I'm going to kind of continually refer to emeries as the basic example, but everything I say applies everywhere in every space-time. If I have a little black hole sitting right here, it's going to behave the way I'm just going to describe now. So we said that we could assume that the exact metric describing this space-time with this little object in it, we were going to write that, I said this in the first lecture, we're going to write this as a background describing this external stuff if the small body was not in the space-time, plus perturbations coming from the presence of the small body. where here epsilon is little mass over the external length scale. So this would be the mass ratio if this were an emery. We said that we were going to do this, but can anyone point to where an expansion like this is not going to work? So this is assuming that the perturbation due to the small object is very small compared to the background metric. Exactly. So if I get really close to the small object in some little region that's comparable to the size of the object itself, this is now a terrible approximation. Because if I'm that close, I'm not feeling the external stuff at all. The external stuff is basically irrelevant to me. This thing right here is pulling me in. It's causing the dominant source of gravity. So in this little region, you should not be using this, except in a certain effective way that I'll describe a bit later. So what we want to do is use a different approximation here. So we need a different approximation in a small region. Let me just, actually keep this down. Let me draw the example of an emery. So we've got big mass, we've got small object zipping by. In most of the space-time, we can use this, with L now being the big mass. Let me call that equation 1. Then in this little region, around the small object, I want to zoom in and consider the second approximation, where I take my same exact metric, but now, rather than expanding around the external background, I'm going to be expanding around the space-time of the small object itself, G object. That is going to depend on the length scale little m, not the length scale big M. So I'm going to have functions of R over big M, whereas here all my things are basically functions of R over little m. Here everything's going to be a function of R over L generically, or R over capital M in the emery case. So think of, say, the Schwarzschild metric. The only way R appears is as R over little m if you're in Cartesian coordinates. If you're in polar coordinates, you have that, R squared just hanging around. So let me say I'm going to be in locally Cartesian coordinates when I'm writing this expression. Then I still want to expand for small epsilon, because it is true everywhere that this is a small number. So I'm going to expand for small epsilon again, but now all my coefficients are going to be functions of this scaled coordinate, R over little m. Plus order epsilon cubed. And I'm going to define this expansion as G bar alpha beta. This is not trace reversal. I'm just saying, okay, this expression, I'm calling that G bar, just because I want to differentiate it from this one, where I'm going to keep calling this G hat. But they're both expansions of the same exact G hat. Okay, now what I'm going to do is matched asymptotic expansions. So matched asymptotic expansions is a classic method in singular perturbation theory. Singular perturbation theory is basically exactly this scenario, where you have an approximation that seems very natural, that then just breaks at some point or in some region in your domain. And so the way you work here is use two different solutions, one in this small region, one everywhere else, and then they need to appropriately match each other. They need to agree in an appropriate sense. Now, the way they need to agree is if you re-expand both of them in a common way, then the coefficients in the re-expansion need to match order by order. So let's say I want to expand that first equation for r much, much less than L. So this is expanding. Let me put a little r here. R here is going to be some representative distance from the small object. So this is not the Schwarzschild coordinate r of the big black hole. This is just distance from the small object. So when I say I want to re-expand for r much, much less than L, what I mean is I'm expanding very near the small object. So I'm taking this approximation and expanding it near this point. And I'm going to take 2, and I'm going to expand for r much, much bigger than the little mass. So this is expanding at distances very far away from the small object. So I first do an expansion that gets me into this region. That's this 2. Put a 2 here. And then I'm looking far away, so like the outer limits of this near zone near the small object. And then here, I'm starting from the outer limits and expanding inwards. So these two re-expansions give me double expansion. So I'm going to write one as a sum of epsilon to the n, g hat n, alpha beta, is a function of r over L. So g hat 0 is what I was just calling g over there, the background metric. G hat 1 is h1, g hat 2 is h2, etc. And then I want to re-expand that when r is much, much smaller than L. So I'm doing a small, and treating this argument as small. Don't know if I'll have room to write it there. So P here is going to be the power of this small quantity. So we have epsilon to the n, r over L to the P, and I'm going to call the coefficients g hat n P alpha beta. And now these only depend on like time, local time along the part of the small body's path, and angles around the small body. I've removed all the r dependence into these powers. Notice I don't specify the range of P. We don't know that when we start. We can have negative powers of r and positive powers of r. So then I'm just going to re-expand 2 for r much, much bigger than m. So 2 I'm going to write as n prime bigger than or equal to 0, epsilon to the n prime, g bar n prime alpha beta. And this is a function of r over little m. Now on to expand when r over little m is very large, or when m over r is very small. So we have n prime greater than or equal to 0, and we now are going to have a sum over p prime, where we have epsilon to the n prime, r over little m to the p prime, times some coefficients, g bar n prime p prime alpha beta, where again these coefficients just depend on local time along the body's path and angles around the body. So now you can see I've got 2 double expansions in epsilon and in r. you can then rewrite them in a common form by saying m is L times epsilon, or by saying L is the other way around. So m is epsilon times L, or we can do L is m over epsilon. So that will then put this double expansion in exactly the same as this one, or vice versa. I can choose which one I want to convert. So what I'm going to do is convert this one. So this combination here is epsilon to the n plus p multiplying r over little m to the p. Right, so I've just written L as m over epsilon, and that was raised to the power p here. So I have epsilon to the n plus p, and then r over m to the p. So now, in this form, these coefficients shifted by p have to be identical to these coefficients. Because I'm starting with the same function g hat in both cases, and I'm just expanding it one way and then back, or back and then the other way. So these two expansions should commute, and so the coefficients should be identical with this shift. N needs to be shifted by p to match n prime. Now I'm not going to go through any details. I'm just going to tell you one thing here, and then we can finish this bit tomorrow. But the main thing is, I mentioned that we don't know the range of p or p prime when we start. But now we can use this matching condition to dictate for us what is the range of p and p prime. So let's look at just this generic term where I've got epsilon to the n plus p times r over p to the m. So generic term looks like this. And this, whatever's multiplying this, has to match a term here. But here, the powers of epsilon start at 0. There are no negative powers of epsilon in this solution, which means that n plus p had better be bigger than or equal to 0. Because otherwise, there's nothing that this term can agree with in the other re-expansion. So that restricts my range of p. So p has to be less than or equal to negative n. Now let me translate that back to simpler looking expressions or more intuitive expressions. Say I start at n equals 0. That's just the background metric, g alpha beta. What this condition is telling me is that if I expand g alpha beta for small r, yeah. Thank you. Yes, thank you. Yeah, that would have made the next few equations very confusing. Okay, yes, thanks. So this is the background, and this is saying if we expand this for small r, then we cannot have any negative powers, so any negative values of p. So if n is 0, p has to be bigger than or equal to 0. So this has to start at order r to the 0. And then we'll have corrections that are linear in r, quadratic in r, etc. Which is just telling you that the matched asymptotic expansions is dictating that the background metric has to be smooth, or at least bounded at this representative trajectory of the small body, r equals 0. Then n equals 1, we've got h1, and we've got p has to be bigger than or equal to -1. So that says when r is small, this starts at order 1 over r. And then we have plus r to the 0, plus linear r, plus quadratic r, etc. Same idea, this just keeps going. h2 starts at 1 over r squared, plus 1 over r, plus r to the 0, etc. So hn starts at 1 over r to the n. So the higher order you go in perturbation theory, the more singular these functions become at r equals 0. There was a question?
So the second expansion is accounting the points of the geodesics? Like the regular equation is already accounted?
So far, we don't have any singularities. So here I'm just treating these as functions. This r equals 0 would be inside the black hole, where it might not be a meaningful point. I'm just saying as functions, like all these expansions are actually outside the small body. I'm actually looking at solutions to the vacuum Einstein equations outside the small body. But just as functions of r, if I continue down to r equals 0, these HNs become singular at r equals 0. But that's not where they're the physical solutions anymore. These are actually only the physical solutions at distances way out here, far away. But if you just say, no, forget that, I'm just carrying those exact same solutions all the way down to r equals 0 analytically, then they'll be singular. But yeah, so far there's nothing needs to be regularized. Everything is perfectly nice, everything's perfectly smooth, except singularity inside the black hole. If it is a black hole, if it's a neutron star, there's no singularity. So far, no regularization. Everything's still the physical fields. Everything's well. Okay. Maybe I'll just point out one last thing. If you have something that's r to the 0 plus 1 over r plus 1 over r squared, with some coefficients, that looks like, for example, the Schwarzschild metric if you expand at large r. And that's exactly what this is. This whole column, carried down to hn plus 1, etc., all the way down, this whole column is equal to the large r expansion of the object's space-time metric. Okay, so I'll end there. Maybe allow a minute or two for questions. Otherwise, we'll pick up still with matched asymptotic expansions, but then I will start talking about regularization. I'll by hand introduce singularities because they're more convenient than not introducing them. And then I will regularize them to make sure I recover what I get from matched asymptotic expansions. So we'll cover that tomorrow.